I want to go over a few theorems about dot products. These will just be properties that will make further proofs easier as we can use these properties and not have to prove them every single time. The first of these being that there is a commutative property, or often called a symmetric property of dot products. That is, the dot product of A and B is the same thing as the dot product of B and A. Thus, the order that we take the dot product doesn't really matter. So to see this in action, we can see that A dot B, right, is defined to be the sum as I goes from 1 to n of AI, BI. Now, because of the commutative property of multiplication, this is simply equal to the sum as I goes from 1 to n of BI, AI. But now by the definition of the dot product, this is equal to B dot A. So therefore, we have shown that A dot B equals B dot A. So the dot product, in this case, is a symmetric operator. The next theorem is that A plus B dot C is equal to A dot C plus B dot C. Now this means that the dot product has a distributive property, similar to multiplication. So to show this, we can just start with our definition. So A plus B dot C is equal to the sum of the ith element of A plus B, whereas when you add vectors, you just add their entries together. So this is simply AI plus BI, and then multiply it by the ith element of C, so CI. And I goes from 1 to n. Now, because of the distributive property of multiplication over addition, we have that this is equal to AICI plus BICI. We've just distributed the C. And this is all in one sum. I equals 1 to n. And of course, we can break up this sum as addition is associative. So this is equal to the sum of, as I goes from 1 to n, of AICI plus the sum of BICI as I goes from 1 to n. And now we simply have the formula for A dot C and the formula for B dot C. So to finish this off, this is equal to A dot C plus B dot C. And hence, proving a very useful property, now we have our distributive property of dot products. The next theorem looks at how vectors and scalars interact when we take the dot product. So this theorem is SA dot B is equal to S times A dot B, which is equal to A dot SB, where we know that A and B are vectors in Rn, and S is a scalar. So let's start with the left part. We have SA dot B. So SA dot B is equal to, so we note that if you multiply a scalar by a vector, all the entries of that vector are multiplied by that scalar. So this will be SAI times BI, right? Where we note the kind of parentheses here, but we have an associative property of multiplication, so these parentheses are really just keeping in mind where they start from, like that. Now, of course, we can change the order of multiplication since multiplication is commutative. So the sum is I goes from 1 to n. So we can take the s out, right? So S, A, I, B, I, right? And then this is equal to S times A dot B. And similarly, we could change the order. Instead of S times A times B, we could have A times S times B, right? So similarly, this is going to be equal to the sum as I goes from 1 to n of AI times S times BI. And we can kind of note, they put the parentheses here. And so then this, by definition, will be A dotted with S similar reasons, right? We see the symmetry. This is going to be SA dot B, and this will be A dot SB. And so this property is really useful because now we have commutativity, we have distributivity, we have being able to pull scalars out. So now we can kind of do a bunch of things all at once when we are doing our future proofs and not have to really worry about it, because the order doesn't matter, where you put the scalars doesn't matter, and we can distribute these things. Our final theorem, this is kind of a cool one in my opinion. This is the positivity of dot products. That being that the dot product of a vector and itself, so A dot A, will be non-negative, and it will only equal 0 if A equals 0. So we say A dot A equals 0 if and only if A equals 0. That's kind of what these two F's are referring to. So if we can think about A being, right, the entries A1 through AN, right? A dot A, right, is going to be equal to A1 squared plus AN squared, right? So squared terms are non-negative, right? Because any number squared is either going to be 0 or positive. So then the sum of non-negative terms will clearly be non-negative. So this is greater than or equal to 0. The only way for these terms to be 0 is if for each of the individual terms, right? So A dot A equals 0, right, implies that each sum is 0, right? Because each term, otherwise it would not be 0, it'd be positive, and none of these can be negative. So AI squared equals 0, right? Which implies that AI itself equals 0, right, for all I. And then similarly, if A equals 0, then A dot A will also equal 0, because each entry will be 0, and then it's just 0 squared plus 0 squared plus 0 squared. So that kind of shows the if and only if. And yeah, so this is our final of the theorems I wanted to show you. So thank you very much for watching.